Hello everyone, my name is Kirti and I am a student of BSc Chemistry Honours second year. This is an audio recorded lecture for visually impaired student on the topic Chemistry of Actinides from Inorganic Chemistry. Actinides constitute a series of elements following actinium with atomic number 89 in the 7th period of the periodic table. Actinides belong to F block as these are formed by the gradual filling of Fs 5s subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides, which follow lanthanum with atomic number 57, involve the gradual filling of a 4f subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. This series of 14 elements is called actinides. Actinides, along with lanthanides, constitute complete F block element. The ending "ide" in actinides is not appropriate because it more correctly means negative ion, such as oxide or chloride. Actinides were also named actinines by a group of scientists. However, the ending "on" is used preferably for non-metals such as boron, silicon, etc., whereas all the actinides are distinctly metallic. UPAC has now recommended these elements to be called actinoids with the ending "oid" rather than being called actinides or actinones. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only naturally occurring actinides named thorium, protactinium, and uranium were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reaction. These elements are named man-made or synthetic elements. Another name coined for the elements is transuranic elements. Transuranic elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspect of chemistry of actinides. First is position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of the noble gas radon as xenon 54, 6s2, 4f14, 5d10, 6p6. After radon, the 7s and 7p orbital gain stability relative to 5f orbital because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new elements: francium with atomic number 87 and radium with atomic number 88 belonging to s block element. After the addition of two electrons in the radon core, the 5f and 6d orbital penetrate the 7s orbital. The least penetrating f orbitals are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium to lutetium enter the 5s shell. It is important to note that around actinium, both the 5f and 6d subshell possesses almost similar energies. Because of similar energies of 5f and 6d subshell, the incoming electron may enter either of the two subshell, which result in the uncertainty of the electronic configuration. As a result, it is doubtful whether the electron enters the 5 orbital or not. For example, the configuration of thorium may be written as either 5f0 6d2 7s2 or 5f1 6d1 7s2. However, once filling start in f orbital and 5f subshell become more and more stable. As a result, from uranium onward, the 5s subshell becomes most stable. Thus, all the incoming electrons start filling progressively in f orbital. The general electronic configuration of actinoids can be as signed Rn 5f 0 to 14, 6d 0 to 1 and 7s2. Next is general characteristics of actinoids. Some of the general characteristics of actinoids are detailed below. First is electronic configuration. As already discussed in section 5.1, the actinides involve the gradual filling of 5f subshell. The electronic configuration of the titled actinium is Rn617s2. Thus, from thorium onward, the 5s subshell start progressively filled. The general electronic configuration of the atom of the actinides in the ground state may be written as Rn 5F1 to 14, 60 0 to 1, 7s2. This is the table for the electronic configuration of the three outer shells of the atom of the actinides in the ground state. Next property is physical property. First is melting and boiling point. The melting and boiling point of actinides are moderately high but are lower than those of the transition elements. An inspection of the table 5.2 reveals that there is no regular trend in the melting and boiling point of the known actinides. This is the table 5.2 with the melting and boiling points of the elements. Third physical property is density. An inspection of table 5.2 reveals that the element near uranium have very high density. Americium resemble the corresponding lanthanide, europium in being less dense than its neighbor. Next property is ionic radii and actinide contraction. The size of the actinide ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is poorly screened by the F electrons. This steady decrease in ionic radii with the increase in atomic number is called actinide contraction. A comparison of M3 positive ionic radii of actinides with those of the lanthanides reveals that the actinide and lanthanide ions are very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ions in case of actinides is shown in table 5.2. It is interesting to note that there is a decrease in the atomic radii from thorium to uranium, which may be due to the increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from thorium to uranium may be considered to consist of Mn positive ions with a total of Ne electrons for atoms. After plutonium, the metallic radius increases significantly again, which may reflect the increasingly lanthanide-like behavior of the later actinides, in which the preferred oxidation state is +3 with only 3 electrons per atom available for metallic bonding. Next property is oxidation state. The actinide element show a greater range of oxidation state than the lanthanides, particularly in the early part of the series. This is the table which show the different oxidation state of actinide element. The +2 oxidation state in case of actinide is very rare. Am2 positive has the electronic configuration 5s7. It is analogous of Eu2 positive in the lanthanides but exists only in the solid state as the fluoride AmF2. On the other hand, Cf2 positive, Es2 positive, Fm2 positive, Md2 positive and NO2 positive exist as ions in solution. The property of divalent actinides resemble more closely to Ba2 positive in group 2. The most stable +2 oxidation state is exhibited by nobelium as NO2 positive and correspond to stable 5F14 arrangement. The +3 oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinide. The first four elements, that is TH, Pa, U and Np, do not show +3 oxidation state as the most stable oxidation state. For example, U3 positive is rarely oxidized in air as well as in solution. Interestingly, the most stable oxidation state of elements up to uranium is one involving all the valence electrons. Thus, the most stable oxidation state of TH, Pa and U are +4, +5 and +6 respectively. Although neptunium show the oxidation state +6 by involving all its valence electron, it is not the most stable state. This is because Np in +7 oxidation state is highly oxidizing and the most stable state is +5. The +4 oxidation state is exhibited by all the element from TH with atomic number 90 and CF with atomic number 96. However, Pa and Np display the most important +4 oxidation state. The M4 positive ions are known in the acid solution and are precipitated by F negative, PO4 3 negative, and IO3 negative ions. The element all from dioxide MO2 and fluorides MF4. The plus 5 oxidation state is exhibited by all the elements from Pa with atomic number 91 to Am with atomic number 95. However, plus 5 oxidation state is most stable for Pa and Np. It is important to note that M5 positive ions do not occur in solution as such. In fact, these states occur as their oxocations such as MO2 positive ions. A few solid compounds are known, whereas in solutions these ions disproportionate rapidly. The plus 6 oxidation state is exhibited by lower actinides in the form of their fluorides. The plus 6 oxidation state is more commonly found as the dioxo ions. The dioxo ions are linear and exist both in the solid as well as in solution. One of the most commonly encountered compound of uranium in plus 6 oxidation state is uranyl nitrite dihydrate, that is UO2 NO3 whole twice 2.2H2O. It consists of linear UO2 positive ions surrounded by two NO3 negative ions and water molecules. The NO3 negative group are bidendant and therefore two oxygen from each NO3 negative are bonded to uranium. Oxygen atom from the two water molecule also bond to uranium, thus the coordination number around uranium is 8. The lower oxidation states are ionic while the higher oxidation states are increasingly covalent. The plus 7 oxidation state is known only in the oxocations of Np and Pu when alkaline solutions are oxidized by O3. The important oxoanions known in case of Np and Pu are NPO4 OH2 with a overall charge of -3. Next property is color of the ions. Actinides ions are mostly colored. The color of a particular actinide ion depends upon the number of electrons present in the 5f orbital. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cation formed by the actinides ion in aqueous solution is given in the table 5.4. In addition to FF transition in actinides, the color can also arise due to FD transition as well as charge transfer transitions. The color of the actinide ion solution because of FF transition occur in the visible and ultraviolet region. We have already encountered this FF type of transition in case of lanthanides as well, since the 5f electron in case of actinides are projected out more in space than the 4f electrons in lanthanides. These 5f electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterize easily. It has been experimentally found that the absorption due to FF transition in case of actinides are nearly 10 times stronger and 2 times broader than the FF transition of lanthanide ions. The energy difference between 5f and 6d orbital in case of actinides being smaller than 4f and 5f orbital in case of lanthanides. The actinides ion inversely absorb light of lower frequency. As a result, the allowed and very strong for FD transition lie in the ultraviolet region and therefore do not influence the color of the actinide ions. It has been observed that the actinide ions in higher oxidation state display predominantly charged transfer spectra. This spectra is exhibited only by high oxidation state ions, which can easily oxidize the ligands. It is important to note that lanthanides do not exhibit charge transfer spectra because lanthanides do not display oxidation state higher than 4. This is the table 5.4 which show color of the actinide ions in aqueous solution. Next property is magnetic property. The actinides show similar magnetic property to lanthanides in terms of magnetic moment with the number of unpaired electrons. This is shown clearly in the graph where the magnetic moment are plotted against the number of unpaired electrons. It is important to note that the high valence state have been chosen to 5f1, 5f2, 5f3 and 5f4 ions, which show the close similarities. Magnetic moment value for the isoelectronic actinide ions are lower than the lanthanide ions. This is due to the fact that 5f electrons in actinides are projected more in space to the crystal field. As a result, the partially quenching of orbital occur by the crystal field effects. Next property is their reactivity. The actinides are highly reactive metals. These react with the dihydrogen and form non-stoichiometry hydrides with the formula MH2 or MH3. They react with hot water and tarnish in air, forming an oxide coating. The actinides react readily with HCl, but reaction with other acid is slower than expected. The metals are basic and do not react with sodium hydroxide. The actinides react directly with the halogen to form a variety of halides. The redox potential for known the M3 positive by M couples are absent are about minus 1.9 volt. Thorium and uranium chemistry has been explained in detail. Some of the general methods for preparing compound of actinides are given below. Next topic is occurrence and isolation of actinides. All the elements beyond actinium in the periodic table are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest naturally occurring element with an abundance of 2.4 ppm in the earth crust. Among the actinides, Th and U occur on the earth because the isotope 23592U, 23892U, 23290Th and 244Th have half-lives sufficiently long in view of the fact that the earth was formed several million years ago. Uranium. Since uranium is the most important of all the actinides, its chemistry will be discussed in more detail. It is primary naturally source of uranium is pitch blende or uraninite, which has the empirical formula U3O8. The mixed oxide containing uranium both in 4 and 6 oxidate state as UO2.2UO3. The other important ore are carontite, iontonite and calcium carontite. Extraction of uranium. As already mentioned, the main source of uranium is pitch blende. The detail of the extraction of uranium involves the following step. First, concentration. The ore is crushed to a fine powder and is subject to conventional gravity separation to remove the lighter impurities. Next is roasting. The concentrated ore is roasted on the earth of a reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic, and antimony. Next is acid treatment. The roasted ore is treated with dilute H2SO4 in the presence of an oxidizing agent such as MnO2 and NaClO3. This treatment converts uranium to a soluble uranium sulfate UO2SO4. The roasted ore can also be converted to a solution of UO2 NO3 whole twice 2 by dissolving the ore in nitric acid. Next is treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of uranyl sulfate precipitate it as ammonium uranyl carbonate. Alternatively, ammonia is added to the solution of uranyl sulfate obtained in step 3. This gives rise to bright yellow precipitate of ammonium diuranate. This precipitate is often called the yellow cake. This cake on heating gives rise to mixed oxide uranium 4 and uranium 6 oxide. Next step is conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. Next step is production of uranium. Elemental uranium can be produced from uranium dioxide by using either of the two methods. A. UO2 is heated with vapors of HF to form uranium 4 fluoride, which in turn react with magnesium to yield uranium metal. Or B. by converting UO2 to a volatile uranium tetrachloride by heating it with elemental chloride in the presence of charcoal. This is followed by reduction with elemental sodium. All the steps detailed above can be summarized in the flowchart sheet diagram for the extraction of uranium. This is the flowchart. Next is chemistry of separation of neptunium, plutonium and americium from uranium. The three elements neptunium, plutonium and americium that follow uranium in the actinide series are produced mainly from uranium in the nuclear reactor. If you recall, uranium is the oldest known element among the actinides. Naturally occurring uranium contains two main isotopes which occurs in the ratio 99.3% and 0.7%. There is another isotope of 23392U which occur in the traces only. Neptunium and plutonium were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutron in the cyclotron in Berkeley, USA. Both the elements are now obtained from spent uranium fuel element of nuclear reactor, which they are formed by the capture of neutrons produced in the fusion of 23592 uranium fuel. This is the reaction. Isotope of plutonium Pu can also be prepared by reaction in which a fast neutron is added with the subsequent loss of two neutrons. Americium can be obtained from the isotope of plutonium by the success reaction in the nuclear reactor. The yield of the heavier element after americium is controlled by two factors. First, the half-life of the various isotopes, and second, by their ability to absorb neutrons. It is important to note that the stepwise addition of slow neutrons is very difficult. A quick method is to bombard the nucleus with a large number of fast neutrons without allowing time for the intermediate product to decay. The separation of these elements from uranium is extremely difficult and hazardous. It is because these elements, including the starting material, are not only highly radioactive but also give highly radioactive fission product. Plutonium especially is extremely toxic. A dose as small as 10 raised to power minus 6 gram may be fatal, which smaller doses are carcinogenic. The separation of Np, Pu and Am from uranium are based on the following chemistry. First, stability of oxidation state. A steady decrease in the stability of high oxidation state with the increase in atomic number have been observed with the increase in atomic number. Separation of these elements from uranium, from fission product and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential and then using solvent extraction or precipitation. For example, Pu can be oxidized to PuO2 positive while Am remains in Am3 positive. Thus, plutonium Pu can be removed by solvent extraction, whereas americium can be precipitated as AmF3. Next is extraction into organic solvent. The MO22 positive ions from solution can be extracted into organic solvents. The M4 positive ions are extremely extracted into tributyl phosphate in kerosene from 6-MHNO3 solution, whereas M3 positive ions are attracted from 1016-MHNO3. Next is precipitation reaction. Actinides in the +3 and +4 oxidation state can be precipitated as their fluorides or phosphate from acid solution. The higher oxidation state beyond +4 give either no precipitated or can be prevented from precipitation by complex formation with sulfate ions. Next is ion exchange method. Ion exchange method are commonly used in separation for small amount of material as in the separation of americium. Spent uranium fuel rods removed from the nuclear reactor can be used to extract Np and Pu in kilogram quantity whereas Am in 100 gram quantities. This reprocessing of nuclear fuel rod is an important technology as this helps to extract new element that may be used as nuclear fuel. Spent fuel rods are dipped in ponds of water for several days to allow them to cool. During this dipping period, intensely radioactive isotope with short half-life such as 150 153I with half-life 8.04 days lose most of their activity. The fuel rods are dissolved in 7-MHNO3 and extracted with 30% tributyl phosphate in kerosene. The extraction coefficient of the actinides in 7-NHNO3 solution containing 30% tributyl phosphate in kerosene are PU4 positive greater than PuO22 positive. The M3 positive ion have very low extraction coefficient in 7-NHNO3. As a result, nitrates of UO22 positive and PU4 positive are preferably extracted in tributyl phosphate, leaving the other actinides, namely NP and AM, along with other fission product in aqueous solution. It is also important to note that 7HNO3 cannot oxidize PU4 positive to higher oxidation state. Thus, PU4 positive is reduced to PU3 positive which enter the aqueous phase, while UO22 positive remain unchanged in organic layer. The separation of other actinides, namely NP and AM, can be achieved by the use of appropriate oxidation reduction cycles coupled with solvent extraction. For example, Pu3 positive in aqueous nitric acid can be oxidized as PuO22 positive by an oxidizing couple with electrode potential greater than 1.02 volt followed by extraction into hexane, whereas Am3 positive is unchanged and remains in aqueous solution. Next topic is the later or heavier actinide element. The element from curium onward, namely curium, berkelium, californium, einsteinium, ferminium, mendelevium, nobelium, and lawrencium, are named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The unavailability of some of the most accessible isotopes are given in the table 5.6. It is clear from the table that curium is available only in macroscopic quantity, whereas the later actinides above atomic number 100 have been prepared only in minute quantities. In other words, later actinides are available in tracer amounts. It is interesting to note that the later actinides show close resemblance to the lanthanides. However, the actinides can be easily separated from the lanthanides because the actinides rarely form complexes. For example, the actinide react with concentrated HCl to form the corresponding chlorocomplexes. If both groups of ions, that is lanthanides as well as actinides, are absorbed on the cation exchange column, the actinides can be eluted more conveniently with concentrated HCl. After eluting the actinides can be separated from each other by ion exchange using citrate solution to elute them. It is interesting to note that the order in which the tripositive actinides ion are eluted show a close similarity to the order in which the tripositive lanthanide ions are eluted. Figure 5.7 display the elution diagram for the actinides and lanthanides element. The first identification of the element from americium to mendelevium on a weightageable or measurable scale was made through elution. All the actinides with atomic number 96 to 103, that is Cm, Bk, Cf, Es, Fm, Md, No, and Lw, with the exception of nobelium, which have oxidation state plus 3 as the most stable oxidation state. The most stable oxidation state of nobelium is plus 2. This is because it has the most favorable F14 electronic configuration. Actinide with atomic number 98 to 102, that is californium to nobelium, also display plus 2 oxidation state. Except for nobelium, plus 2 oxidation state is strongly reducing in nature. Higher oxidation state of curium are found in the solid state in the compounds such as CMF4 and RbCamF3. Similarly, berkelium compounds are stable in the plus 4 oxidation state such as BKO2 and Ca2BKCl6. Lawrencium exists only in the plus 3 oxidation state and resists oxidation and reduction. The element up to atomic number 100 undergo radioactive decay mainly by emitting alpha particle or beta particles. The later element become increasingly unstable as the atomic number increases. Nobelium is excessively unstable and has a half-life of only 3 seconds. Next topic is element beyond atomic number 103. The actinide series is complete at lawrencium. We have already learned that the half-life of the later actinides beyond atomic number 100 decreases considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that the half-life of element will decrease further as new and new elements are discovered. A major controversy came to light over naming these elements. The choice of the name of the element belonged to the discoverers. In case of three nuclear facilities are in competition for the synthesis of each of the now newly discovered element. The facilities are at Berkeley, California, USA, Dubna at Russia, and Darmstadt at Germany. It is extremely difficult to identify which nuclear facility had the true claim. For example, the discovery of element 104 was claimed by the both Berkeley and Dubna groups. The Americans named the element Rutherfordium, while the Russians named it. While these conflicting claims were being settled, the International Union of Pure and Applied Chemistry devised a hybrid Latin Greek numerical system of providing provisional names and symbols to all the newly discovered elements. The names of the derived directly from the atomic number using roots for the three digit in the atomic number of the element and adding the ending IUM, the root of the number and their abbreviation are given in the table. In some cases, the names are shortened by removing the repetitive letter. Bi plus IUM can be written as PIUM or tri IUM can be written as tri-UM. Let us name element with atomic number 106 according to hybrid Latin Greek nomenclature. This is the table for nomenclature of element with atomic number above 100. Next topic is comparison of actinides and lanthanides. Both lanthanides and actinides constitute element of F block as these involve the gradual filling of F orbital. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their property but also differ in many property. Let us review some of the important points of similarity and dissimilarity among the lanthanides and the actinides. Point of similarity: both the lanthanides and actinides involve the filling of f orbital. Both the lanthanides and actinides display predominantly plus 3 oxidation state in most of their compound. Due to poor shielding of 4f and 5f electron, both lanthanides and actinides show gradual contraction in the size of their atoms with the increase in atomic number known as lanthanide contraction and actinide contraction respectively. Element of lanthanides and actinides with the same number of unpaired electrons display similar absorption spectra due to FF transition. Lanthanides and actinides are highly electropositive and are very reactive. Nitrate, sulfate, and perchlorates of trivalent lanthanides and actinides are soluble in water. Both lanthanide and actinide can be separated by ion exchange method. Now, point of difference is lanthanide involve filling of 4f orbital and actinide involve filling of 5f orbital. Lanthanide have energy gap between 4f and 5d orbital is large. As a result, their chemistry is fairly similar. The energy gap between 5f60 in actinides is small. As a result, their chemistry is very different. Binding energy of 4f orbital are higher in lanthanoids and binding energy of 5f orbital are lower in actinides. The most common oxidation state is plus 3 in addition to some lanthanide showing plus 2 and plus 4. The most common oxidation state is plus 3 in addition to some actinide showing plus 2, plus 4, plus 5 and plus 6. Lanthanoid do not form oxocation, actinides form oxocation. Most of the lanthanide are colorless, most of the actinides are color. Lanthanides have tendency to form complexes small, actinides have a greater tendency to form complexes. Compound in lanthanides are less basic in nature and compound of actinides are more basic in nature. So this is all about the chemistry of actinides. I hope you liked this audio recorded lecture. Thank you all.